Random forests are implemented in Python, more specifically in scikit-learn via the classes random forest regressor to handle regression problems and random forest classifier to handle classification problems. We will now see the list of all the hyperparameters to specify when building a forest. The number of trees and estimators is a first hyperparameter set by default to 100. The impurity criterion used to build the tree can be changed via the hyperparameter criterion. By default, Gini is used for classification and the variance for regression. Different hyperparameters are then used to specify the structure of the tree. By default, the trees are fully grown. The simultaneous use of default values for all these hyperparameters leads to trees with only one observation per leaf. By default, no pruning strategy is used. The number max features of variable preselected to split in each cell can also be changed. By default, it is set to the square root of the total number of variables in classification. Be careful, by default, in regression, no randomization is performed on the splitting directions. In regression, the chosen split is the one maximizing the splitting criterion according to all the variables. It is also possible to use the whole dataset to build each tree, i.e. to suppress the bootstrap step via the bootstrap = false command. By default, the bootstrap step is present. It is also possible to generate smaller bootstrap samples containing max samples observations via the parameter of the same name. Several remarks related to these hyperparameters can be made. Because of the bootstrap and randomization steps, the random forest algorithm is a random algorithm. Running the random forest algorithm twice on the same dataset can lead to two different predictions. Indeed, during these two executions, the additional randomness will not be the same, the constructed trees will not be the same, and the final predictions will differ. It is possible to fix this randomness via the random state hyperparameter. This is particularly useful in a preliminary debugging phase because it allows to compare the outputs of two executions of the algorithm, both using the same value of random state. Another way to limit the variability of predictions between two executions is to increase the number of trees. The randomness of the forest algorithm can be a problem in practice. Indeed, it means that applying the algorithm several times to the same dataset can lead to different predictions, and thus different recommendations. This is particularly dangerous in a decision support framework for sensitive domains such as health or public policies. For these reasons, it is preferable to set the random state to an arbitrary value or to increase the number of trees so that the prediction of the forest do not vary in the first case or the variations are attenuated in the second case. Note that one value of the random state hyperparameter may result in two different predictions if the algorithm is run on two different machines. By default, the randomization of the cuts is only used in classification. In regression, removing the bootstrap step leads to a deterministic algorithm without any additional randomness. This means, in particular, that all trees are identical within the forest. The forest is thus reduced to a single tree, which is not desirable. Therefore, in regression, we will always keep the default bootstrap step, or we will explicitly specify a randomization of the cuts. Let's try to focus now on the role of each of the hyperparameters. The number of trees is the simplest hyperparameter to set. A large number of trees leads to high stability of the prediction of a random forest between two runs. The stabilization effect due to bagging is more important when the number of aggregated estimators is high. Building a forest with a large number of trees is therefore beneficial from a predictive performance point of view, but is costly in terms of computation time. The training time of a forest is proportional to its number of trees. A high value to ensure the stability of predictions and a reasonable computation time is therefore recommended. The default values of the order of few hundred trees generally provide good performances. Precise optimization of this parameter is not necessary. Performances do not change drastically once this number is high enough. The hyperparameters allowing to modify the size of the bootstrap sample and the shape of the tree are more complex to optimize. Indeed, the optimization of these parameters results from bias-variance trade-off. Let's take the bootstrap sample size. By choosing a small bootstrap sample size, the trees will be very different from each other, but will not contain many cuts, which is equal to the bootstrap sample size minus 1. The forest will then have a high bias, the trees being not very complex, but a low variance, the trees being very different from each other. Conversely, if the whole dataset is used for each tree, trees are fully developed, with a low bias, but are exactly the same, and thus have a high variance because the forest reduces to a single tree. Optimizing the size of the bootstrap sample is therefore a matter of choosing the best compromise between bias and variance. In concrete terms, we are looking for the value leading to a low risk on the test set. The same is true for the hyperparameters representing the structure of the tree, for example the depth. By choosing a low depth, we obtain a forest with a high bias but a low variance, because each cell contains a large number of observations. Conversely, if the depth is maximal, the bias is low, but the variance is high. Optimizing the depth means, once again, finding the best bias variance compromise. In practice, this means looking for the value of the hyperparameter leading to the smallest error on a test set. If we know a priori that the training data are highly noisy, we will tend to prefer small bootstrap sample sizes or shallow trees in order to obtain a forest with a non-negligible bias but with a low variance, allowing to reduce the noise of the data. Conversely, if we know a priori that the relationship between the output variable and the input variables is complex, we prefer to use the default setting of the forest with a low bias, even if it means having a slightly higher variance. In practice, information on the level of the noise or the complexity of the phenomenon is difficult to obtain and often comes from a priori or from external knowledge. It is often not useful to optimize both the size of the bootstrap sample and the tree structure. You can set one of the two parameters to the default value and optimize only the other parameters. Similarly, it is not necessary to optimize several parameters encoding the tree structure. Optimizing one of these parameters, setting the others to their default values, is sufficient. The number of directions pre-selected in each cell to cut is the most difficult parameter to tune and whose impact on predictive performance is the least well understood. Fine-tuning of this parameter can lead to clear improvements in predictive performance. If a small value is chosen, for example max feature equal 1, the splitting directions are drawn uniformly in each cell. Trees are therefore very different from each other. Conversely, if a large value is chosen, for example if max features is equal to the total number of variables, the splitting direction is chosen among all the initial directions. The trees are then very close to each other in terms of structure and therefore of predictions. This parameter allows to control the diversity within the trees of the forest and thus to improve the gain brought by the bagging procedure, which works all the better as the individual predictors are different. However, beware that when using max feature equal 1, the diversity is maximal, but the direction of the splits are not chosen according to the data. The resulting trees are very different, but potentially not very predictive. For this reason, the optimization of this parameter is often complex. The use of a test set to find the optimal value of this parameter is to be preferred.